So we have today, and then it's the Thanksgiving holiday break, followed by one more week of classes, and then that's it for the semester. So I will announce the final project on Tuesday when you return from Thanksgiving, and that's going to be it. Project-wise, the final project will be your final exam, and so I'll talk about the parameters of that. It will involve synchronization, so please make sure you have caught up with the reading. Okay, so today, why don't we get started? Today, we're going to continue on with synchronization. And to jar your memory, there's the reading. Please make sure you're keeping up. But to jar your memory, we talked about Peterson's solution. And we talked about this idea of having two variables, one that determines if it's each process's turn to enter the critical section, and another, a Boolean, to represent whether or not it desires to, if it's ready to enter the critical section. Just because it's your turn, it doesn't mean that you are ready. And so using those two solutions, those two variables rather, Peterson's solution guarantees these 3 points that you need to solve the critical section problem. And those are mutual exclusion in that only one process at a time or thread at a time can enter the critical section. And as we saw from the example last time, if two variables are interacting with the data structure, they can arrive upon different ideas or unstable results. Each process can have a different understanding of what the resulting value of that variable could be. And you can imagine for applications like banking, if you're trying to compound interest and at the same time, for example, also apply a balance, you can have some very serious consequences associated with not protecting your critical section. And so this mutual exclusion is really important. It says that only one process at a time can enter the critical section and therefore modify the data structure. There's also the second point, the progress requirement, in that if you have a number of processes or threads, that all of them are making progress. So no process or thread gets starved out from its interaction to the critical section. So you can imagine if you have a high performance web server on the back end and say that's for some electronic commerce website, you have a lot of processes and threads, for example, modifying the database. Let's say in your database, you have an entry representing the number of items that you have in inventory. So let's say, someone's buying an Xbox and they have 10 units of this Xbox in inventory. You could have multiple processes decrementing by one this inventory level every time somebody makes a purchase, right? So it's important for all threads to make progress because you have more than one thread that wants to interact with that particular critical section. And then this third part, bounded wait. Bounded wait says that eventually you will get access, you being a process, or each process will get access to the critical section. So that means is that there's no starvation, meaning that you don't ever get to examine the critical section or interact with the critical section. And so, for example, if you have 10 processes and it takes some time for each process to interact with this critical section to modify some shared data structure, that means for each process, it has to wait for the 9 other processes to be done with it in the worst case before it has a chance to execute. And so there is an upper bound on the amount of time that you must wait, but that means eventually you will gain access to the critical section. Okay, any questions about this? Okay. So let's continue on, and we'll look at hardware mechanisms in place for implementing this synchronization. And so a lot of systems provide hardware support for critical sections, right? And what we'll see is there are specialized instructions called atomic instructions, and I'll talk about that in a few more slides. But all the solutions that are in place implement the idea of so-called locking, right? When you lock something, that means that you have exclusive use to it and no one else can gain entry. So, let's take, for example, you go to like a coffee shop and say, hey, can I use the restroom? They give you this big key on some big dongle, and you go and you use that key to unlock and lock the bathroom door. Now, that bathroom is akin to a data structure, a critical section. And while you're in there, someone else comes along. Well, they cannot access that lock because they can't open it, right? And so for that period of time, the person that unlocks it and uses it, right? They lock it. No one else can gain entry. And then that person who's now using that shared resource, once he or she or it, if you're talking about a process, is done with that resource, it gets explicitly unlocked. So you have this notion of a key or some sort of item that you use, and you can use that to secure that particular shared data structure or critical section, and no other process or thread can access it until you explicitly release it. So that's the idea of a lock. And so for a uniprocessor machine, one way you could implement it is by disabling interrupts. Because if you think about it, if you disable interrupts, what happens? Well, no one else can make progress, including kicking you off the processor. Now, that might sound like a pretty dangerous thing to do, but that's one idea early on that people had for implementing this locking. And the idea behind this locking is that while you're accessing something, no one can kick you off or no one can interrupt what you're doing. And so what this means is that if you are running code concurrently, you're sharing the processor, that means that you would run or execute without preemption, right? And so if you're interacting with a data structure and no one else can grab the processor, you can't be kicked off the processor by nature of how scheduling works. If no other, someone hearing a, oh, it's the next door. All right, it's weird. It's pretty loud. It's the ventilation system. Um, by nature of how scheduling works, until you're done with the critical section and decide, okay, I'm done. Let me now release the processor. No one else can interrupt your access to that critical section, right? But that's a pretty heavyweight solution because you're now kind of breaking concurrency in order to achieve this result, this exclusive use of a shared data structure. And this is very inefficient, right? In particular, it's very inefficient on the multiprocessor because on a multiprocessor system or even a multi-core system, you have multiple threads if it supports hardware threading, and certainly multiple processes that execute physically in parallel, right? And so if you're going to disable interrupts, you have to disable interrupts for every process because you can't just disable it for one processor. And that means you're going to be throwing away cycle time on all the other CPU instances. So this is very inefficient on multiprocessor systems. And for most operating systems, this is not broadly how it's implemented, but it will work if you only have a single processor. Okay, so modern machines approach this locking implementation using something called atomic instruction. And the word atomic in atom in chemistry or physics, depending on which version of physics you took, is the most fundamental unit of matter. It can't be further subdivided. Now, I'm not talking about muons and quarks and all that other stuff, but in terms of the composition of compounds of matter, atom is the indivisible unit, right? And as such, a so-called atomic instruction is indivisible as it pertains to its execution on the processor. And so if you look up any chip specification, and I encourage you to do that, you go look up whatever Intel processor you have on your machine and do a Google search for the atomic instructions, and it'll tell you what those instructions are. And atomic instruction, when your program executes these instructions, it will not be preempted. It doesn't matter if it's the kernel that says, hey, your time on the scheduler is done, you'll be allowed to finish execution of these special instructions, the so-called atomic instructions, right? So indivisible as it pertains to instructions, i.e. atomic instructions, are those that cannot be interrupted, and modern processors have a handful of them specifically for use in the implementation of these locking mechanisms. Okay? All right, any questions about this? Make sense? And so we'll go over the two major flavors. And so the two major flavors, either test memory and set, it's called test and set instruction, and the other is called examine and swap, right? So you can either test a value and set it, or examine and swap. And if you think about it, this value, it could be a Boolean, it could be an integer, and what you're testing and setting to see things like, oh, did someone else grab the lock? And if it's a Boolean, true means that someone else has the lock. False means that they don't have the lock. But if you're going to set these values, these special variables, you need some way for the processor to say, don't interrupt this. And if you don't interrupt it, that means if two processes or threads are trying to grab the lock at the same time, only one will succeed, right? Because the first one to execute that atomic instruction, test and set, the other one's going to have to wait, bless you, um, because this is an atomic instruction. And once the atomic instruction completes, the lock will be grabbed. The next process will come along and say, well, that lock has already been engaged. Okay? And so the test and set and the swap are the two different flavors, if you will, of atomic instructions that modern CPUs and processors have. Okay, and don't take my word for it. Google search it for the CPU in your machine and find out for yourself. And they're typically assembly language. And in most modern languages, when you use the synchronization mechanisms, the machine code that's generated by the compiler includes these atomic instructions, and that's how you implement locks. Okay, and so what does the procedure look like when you're trying to access a critical section through this now locking mechanism? So let's say you're in a tight loop and you have a critical section and you have the remainder section. Before you interact with the critical section, the shared data structure, you acquire the lock. So that's going to involve this test and set or this examine and swap command, atomic instructions. And then you enter the critical section if you are able to acquire the lock, right? So this acquisition of the lock is going to act like the same barrier that we talked about before. Your execution cannot get past that unless you successfully acquire this lock. Excuse me. So then if you acquire the lock after you're done executing in the critical section, interacting with this shared data structure, it's your responsibility to release the lock. So you can imagine if you did not release the lock, this thing is now taken and no one else can make progress. But in some systems, there are some mechanisms in place. So if the process exits, it releases all of its locks, or some facilities for timing. But we're not going to talk about that in this example, just making you aware of it. So you explicitly acquire the lock and release the lock, and then execute your remainder section. And so if another process comes along when you're executing in the critical section, you being the process that has acquired the lock, the other process will block, right? It can't get past that barrier. And there are different ways of blocking that we'll talk about, but up to this point, we've talked about these so-called spin locks, right? You have a while loop that's empty, and you just keep executing the while loop. While your execution is not making progress in terms of the instruction stream, i.e. entering the critical section, you're still executing, right? The thing you're executing is just not doing anything. You're just looping. And underneath the covers, a loop is just a comparison and a jump statement, right? Okay. All right, any questions about this? All right. So let's take a look at the test and set instruction. And this is pseudocode, but typically when you see a test and set, you're going to see assembly language code. So you're going to see load a register, you're going to see a comparison command, and you're going to see a jump if command, right, at that level. And so the test and set, it takes a target, so that's the variable on which you're going to be doing the test and set. You make a copy of the current value, and then you set it equal to true, okay? And then you return what the old value was. So you can imagine if you have a variable, a Boolean called lock, right? You have a pointer to lock, a variable, and what this thing does is it says, okay, well, what's the current value? I'm going to return that, but I'm going to also set it to true, right? So if the lock started out 0, it's going to return a 0, but the new value of that variable is going to be 1 or true. Okay? Now, it just so happens because this is an atomic instruction, this function will complete and return without being preempted. So let's say you're scheduled first come first serve or round robin or what have you, and the quantum of time in round robin expires, and it now says, okay, you have to get off the processor. Well, if you're executing this test and set, you will not be preempted until this value, until this function returns. You're guaranteed that because it's implemented using atomic instructions. So this is executed atomically, and it returns the value of the parameter, its original value that was passed in, and you do that by reference through a pointer. And it also sets the new value to true. Okay, so you can imagine this as a locking mechanism, and you're allowed to lock this variable, i.e. set its value, acquire the lock or lock the lock, without being preempted. right? And this protection from being preempted is afforded or implemented because it's in atomic instructions used to implement this, not because you've disabled interrupts. Okay? All right. Any questions about this? All right. So this is a solution that you might have to implement locking. So here we have the same do while loop, right? We have the acquire the lock here, this while loop, and then we have the release of the lock. You're setting that variable to false. And so in this particular example, lock is a Boolean variable. It starts out, say, as false. And then here in this tight while loop, we have this test and set, and we give it the address of this lock Boolean, right? And so this test and set, as we said, if lock started out as 0, it's going to return a 0, right? So what happens when you say while false or while 0? Well, you go past the while loop. And what's past the while loop is this critical section, and that's your grabbing of the lock or acquiring the lock. Now, the other thing that test and set does, it returns the current value of lock. If it started out as 0, it also sets it to true. So it sets it to true, it returns a 0, and the first process that gets to this critical section is going to be allowed to proceed, i.e. it grabs the lock. Now, the next process that comes along, lock is now true. And when it executes test and set, well, it returns the current value and sets it to true. If you set something true to true again, it doesn't change the state, right? So lock is still true, and it returns true. And if it returns true, you have a while true here, and you continue executing the while loop for the second process that comes along. So the second process is sort of stuck at this while loop. And the only thing that can make it unstick, if you will, so it can proceed, is that first process is done with a critical section and sets lock equal to false. Okay? Does that make sense? Any questions about this? Now, this is a basic implementation, and most modern language implementations for synchronization, it's not done this way, but we still have to kind of develop the idea of spin locks, and then we'll talk about mutexes, semaphores, and monitors. Okay, all right. So the first process to execute it grabs the lock, and then it releases the lock, and the next one, somebody wins. And somebody always wins because this is an atomic instruction. No two processes can execute it at the same time because the process that gets there first in executing the test and set, it is not preempted, so it's allowed to complete this function test and set. Okay. So let's look at the other atomic instruction. And again, it's usually assembly code, but they do it in C pseudocode because it's a lot more accessible, easier to understand what it's doing. So compare and swap, as the name implies, it takes a value or variable. In this case, it's pointed to integer. And it records that value, so makes a copy, and then it compares it to some other parameter. So what it's doing is saying, are you equal to this value, right? And when it makes that comparison, if it is equal to a certain value, right, expected value, then it goes ahead and sets it to a new value. So it's saying, if you're equal to this, then set it to that. So you can imagine for a lock, you'd say, if you're equal to 0, meaning that no one has the lock, go ahead and set it to true, right? Or go ahead and set it to some desired value to grab the lock to indicate to other processes that you want to acquire this lock. And then after that, it returns back the original value of the variable's interest in this return temp statement. So this compare and swap is executed atomically, right? Meaning that this entire function will complete and return its return value without being preempted, right? It will not be preempted. So the first process or thread to execute this, it will be allowed to execute this to its completion, this function, without being preempted, even if the quantum expires. It's an atomic instruction. Okay, and so it returns the original value of the parameter that's passed, here value, and then it sets it to this new value if it's equal to this expected value. Okay, all right, any questions about this? All right, so here's an example of the critical section locking, excuse me, implemented using the compare and swap atomic instruction. So we have, again, a tight while loop here, while true, and we have our critical section and the remainder section. And then here we have a while loop and its empty statement, here's semicolon, and we execute the compare and swap. And so it gets a pointer to lock. So this lock variable is a Boolean, can be 0 or 1, true or false. And it's comparing it to see if it's 0, right? That means, is the lock available? Has someone locked it already? If someone has not locked it already, it'll go ahead and set it to 1. So it'll acquire the lock. And then after that, it'll return the value that lock used to have before it set it to this 1. Okay? So if it was initially 0, it sets it to 1 and returns back a 0 or false. And so this while will exit, and execution will come down here to the critical section. Once it's done with the critical section, it sets that lock to 0, freeing up access to the critical section for the next process. So let's say the first process to execute this compare and swap came in. It saw that lock was initialized to 0. It compares it to 0 and returns a 0, so it proceeds with its execution. The second process or thread that comes along, well, at that point, lock has been set to 1. It does the compare and swap. It says, is it equal to 0? No, right? It does not set it to 1, but it returns the original value, which the second process sees this value as 1. Well, it gets back a 1. This is allowed to finish executing. So it's a while true or while 1, and it continues in this while loop, a spin lock, right? And its execution, the second process, does not get past that while loop. Now, once the first process frees up the lock by setting it to 0, this returns a 0, and it comes out of the while loop, and the second process is able to execute the critical section. Okay. Any questions about this? Does that make sense? Okay. So this is with this compare and swap. And some processors implement one or the other. You might find a processor out there, it's not inconceivable that they'd implement both of them. It's all just a matter of taste and what the designers of the silicon thought would be a good version to implement. Okay, so let's look at this idea of Peterson's algorithm that has these properties of mutual exclusion, bounded weight, and progress using the atomic instruction. So in this particular example, it's using test and set. And to remind you about Peterson's algorithm, it had this idea of a turn variable, and it also had a variable that was a Boolean that encoded whether or not a process was ready. So here we have waiting is true and we have key equals true, and they're changing the variable names. And these two variables, this array of waiting and key, are used to determine whether or not that you desire access to the critical section and whether or not you actually have the lock. Okay. So here we start out, we initialize waiting to true, meaning that the particular process, the ith process, wants to gain access, and key is equal to true. All right. So we start out, we have a while loop here. As long as you're waiting and as long as somebody has the key, then you're going to do test and set, right? Now this test and set is atomic, but it's using this lock to determine whether or not you're going to have access, right? And so this lock can be true or false. And if you get past this barrier, this is a type of spin lock, your execution then goes to enter the critical section. And so now, if you're in the critical section, you're no longer waiting. So you're signaling to all the other processes that you're not waiting. You're currently in the critical section or getting ready to do something in the critical section. Okay, so now then you do a little bit of arithmetic to change an integer that looks kind of like a turn variable, right? And so you take this j and you set it equal to your process number plus 1, and you do the modulo n because you have n many processes. So then after that, you go into this other while loop, and then you're going to sit there and you're going to do another spin loop. You're going to wait again, right? And what you're waiting for is after you execute your critical section, now you're trying to say, okay, when it's my turn again, I'm going to go ahead, I'm going to release the lock, right? So here, when it's your turn again to execute, you get past this other spin lock, and then you set the lock to false, you release things, and then you come back around. Okay. Now this is a little bit more confusing, but what it does introduce is this idea that after you're done with a critical section, you still release the lock, but you can also kind of wait in line for that to happen, right? So we're going to remember that idea that you can have multiple processes waiting in line associated with the management of a lock as it pertains to access of a critical section. Does that make sense? And please remember that because when we talk about monitors, we're going to introduce this idea of condition variables, which is what happens in Java. Okay, so let's take a look at the three major methods for doing synchronization. We talked about this idea of the critical section problem. We talked about Peterson's solution, which is more of a theoretical approach that teases apart the critical section problem as solution to the critical section problem as needing three different properties. You have this mutual exclusion, you have this progress, and you have the bounded weight. So let's take a look at the three different constructs that accomplish this in modern systems. And so mutex stands for mutual exclusion. And what that means is that for any two pairs of processes that want to access a critical section, only one at a time can access them. And so many of these solutions, like Peterson's solutions, can be very complicated. And so often when something's complicated, there are services provided for the programmer or software engineer to make it a little easier. And those services are presented as APIs in a particular language of implementation. And so this critical section problem or solutions to it have been provided by operating systems engineers, and you access these APIs through a language binding or through a set of constructs in the language. And so the simplest is a mutex lock, and this mutex has two different major functions. One's called acquire, that's to grab the lock, and one's called release. So these would be system calls, and these system calls make use of the atomic instructions, and they're accessed through some function call available in the computer language of interest. Okay, so the calls in the implementation of the runtime, the definition of these functions, this acquire and this release, the implementation has to be atomic. So that means you're going to use the atomic instructions inside the definition of acquire and release because you want to make sure that these are not preempted, right? So the access to the lock itself, both the locking and the examination of the lock, is going to be atomic. Okay, and so this solution requires what's called busy wait. And when we saw this while loop that just did nothing and execution didn't get past that, that's called busy waiting. And it's called busy waiting because you're waiting, i.e. you're not accessing or entering the critical section and interacting with that shared data structure, but you're still busy, meaning that you're still executing instructions. Now you might think, gosh, well, isn't that a waste of the CPU cycles? Yes, it is. But the thought is that you're not going to be busy waiting for very long, right? And sometimes in the literature, you'll see the term spin lock, right? And spin lock means the way you implement locking or these barriers is by these while loops that prevent your execution from proceeding. Okay. All right. Any questions about this? Make sense? All right. So let's take a look at this busy wait. Okay. This acquire and release. So you start out and you acquire the lock. Okay. And either you can acquire it or you can't acquire it. If you can't acquire it, your execution proceeds past the acquire system call. If you cannot acquire it, your execution does not proceed past the acquire lock. You enter the critical section, and then you are explicitly, if you're able to access the critical section, you must explicitly call the release so that the next process or thread can come along and interact with the critical section. So here we have pseudocode for the acquire function. And again, these will be implemented using the atomic instructions. You have a variable of interest whose access you protect using atomic instructions. And so you check to see if that variable is false, meaning that no one has the lock. If it is false, you're busy waiting. So execution for a process that calls acquire that does not grab the lock, it will not return until that lock has been released. Okay? So then a process that is executing the critical section, it's going to call release. Available is now true, and the one process that is blocked, busy waiting, or in the spin lock is going to proceed outside of the acquire call. It's going to return, and then it's going to enter the critical section, this next process. Okay? Any questions about this? So this acquire and release would be implemented as system calls available to the programming language through the system call interface by the runtime associated with the kernel implementation. Okay. So let's take a look at semaphores. Now, of course, when we did this mutex, right, it's one process enters the critical section at a time. The process that called the acquire must explicitly release. And the semaphore builds on that. And you'll notice with the mutex, you can only have one process at a time executing. But what the semaphore does, it opens it up. And maybe you have a bunch of shared resources, but you only have enough for, say, 5 processes to use. Now, in that case, sometimes you want a lock where you can effectively define the number of copies of resource that you have. And in that case, if you have 5 copies of a resource, that means 5 processes can interact with those resources. And then if process number 6 comes along, it is now excluded from accessing those resources, those shared resources. And so the idea of having a defined number of resources and you're locking access to that defined number of resources is what is solved by a semaphore. Okay, so with a semaphore, use a synchronization tool. It's more sophisticated than a mutex. A mutex is only one access at a time. Only one person can use the resource, but a semaphore includes a counter and allows you to access some number of copies of a resource as defined by the initialization of that counter. And so a semaphore has an integer variable, a semaphore variable, and that variable, what we'll see in the pseudocode, is decremented every time someone enters the critical section, and it's incremented every time someone does the release, right? And so that variable, when it's initialized, it starts out as 0, and then as it gets more and more and more negative, the magnitude of that negative number describes the number of processes that are in the critical section. Okay, and so you have 2 atomic instructions, the wait and the signal. If you look at the older operating systems literature, you'll see, I think it's Dutch, and it's called the P function, which is wait, and the V function, which is signal, and P is, I think, is Probeeren and Verhoeven, right? And so, I just want to make you aware of that because when you read the OS literature, I think Vrij University in the Netherlands, they did a lot of early work in synchronization. Andrew Tannenbaum, in particular, later Franz Koszowiak, that was at MIT. But nonetheless, you have this wait and the signal, and these are atomic instructions. And the wait is the one that grabs the resource, acquires the lock, and the signal releases the lock. But in this case, this lock variable, instead of being Boolean, yes or no, you can enter, you can't, it's an integer, right? And so now with the semaphore, you're associating a number of copies of resources with your critical section, and therefore you're allowing a fixed number of processes access. Okay, so this is what the wait looks like, the program. And you'll notice this wait, it's associated with a semaphore variable s. And when we come inside, you're checking to see if it's negative, right? Is it less than equal to 0? Well, as long as you're less than equal to 0, you're going to busy wait, meaning that you're going to block. That means all copies of this resource have been handed out. And of course, the more negative S is, that connotes the number of processes that are currently waiting for access. So suppose you have some resource. It could be, I/O devices. It could be whatever it is. And you only have 5 of them. You want to allow processes to interact with one of the 5. So that means once the 5th process enters, the 6th one has to wait. The 7th one has to wait. The 8th one has to wait. And so what you notice here, let's say this S starts out as value 5, right? So the first process comes in. Is it less than equal to 0? Is it less than equal to 0? Nope. It does not. Its execution does not stop at the spin lock, at the busy wait. So then it decrements S. And in that case, if S starts out as 5, the first 5 processes to do this wait, this acquisition of the lock, they're going to be able to proceed. So now the 6th process comes along, the value of S is 0, and this while S less than or equal to 0 is true. So that means the 6th process, its execution is going to stay here. It's not going to be allowed to proceed past the wait call or the acquisition of the lock. And so a semaphore is a type of lock that has a bound on it, and that bound describes the number of processes that are allowed to enter the critical section. And it just so happens that with a semaphore, you can implement a mutex.
A mutex is nothing more than a semaphore where S, the number of copies of the resource of the critical section, is equal to 1, right? Does that make sense? Any questions about this? Now, of course, this is in pseudocode that's eerily similar to C code, but this would be implemented in assembly on most systems. Okay. So then the converse, let's say you have 5 copies of the resource. Each time a process is done with its copy of the resource, it does the release, the signal, and that ends up incrementing S, thus freeing up one of the copies of the resource. So what happens? S, say, started out as 5 processes called wait. S is now 0. Each of those 5 processes is in the critical section using 1 copy of the resources. So that means no more resources are available in the critical section. And now the 6th process comes along, calls wait. Its execution is busy waiting at the spin lock. Now, let's say one of the 5 processes that has a copy of the resource, it calls signal because it's done with its copy of that critical section resource. S now increments. Now it was 0 for the 6th process. It's now 1. One of the processes is going to unblock, go past this spin lock, and now decrement S, right? Question. S, it is a critical section itself, but it's used by the semaphore to um, represent the number of copies of critical section resources. And because this wait and the signal are atomic instructions, S will not have weird values because multiple processes are accessing it. Okay? All right. Any other questions? And so, yes, technically S is a critical section because multiple processes are going to be incrementing and decrementing, but because the modification and testing of S is inside an atomic instruction, you don't have to worry about different values of S being understood by the processes. Okay? All right. Does that make sense? All right. And so yes, the mechanism itself that implements the synchronization lock, it itself is atomic. Okay? And I probably didn't say that before. All right. So let's take a look at semaphores. You can have a binary semaphore. And with a binary semaphore, S, the number of counts of copies of the resource in the critical section is equal to 1. And that behavior is exactly what a mutex does. With a mutex, when you acquire the lock, no one else can use it. When you release the lock, someone else can use it, this critical section. Now, a counting semaphore, it's called a counting semaphore, where you initialize this S, this count variable, to some value, some positive integer, that represents the number of copies of a resource in the critical section. And then once you do the acquire, it decrements because you're using 1 copy, and then another copy, then another copy. But once the number of copies goes to 0, that is freely available for use, then the next process that comes along, it blocks. And so excuse me, the example I gave in the previous slide where I assumed that S was equal to 5, that's the counting semaphore version. And then where S is equal to 0, that gives you behavior of a mutex. Okay? All right. Any questions about this? Does that make sense? Yeah. Now, I'm going to skip those slides, and that was the version of the slides, I think that's on the blackboard, the slides that talk about the implementation of them, because I don't expect you to implement them. I'm just going to focus on how you use the programmatic APIs, because that's where the final project is going to focus. Okay, so one of the observations with semaphores, yes, it allows you to have more than 1 copy of a critical resource, right? And it allows you to set finite bounds on it. And then once these bound of resources violated, any subsequent process that comes along is blocking, right? It's busy waiting. But you notice here, that busy wait is still executing CPU cycles, right? So instead of doing this busy wait, what if you could actually physically have the process wait, right? And we'll develop that idea when we talk about monitors. So let's talk about semaphores. One of the things that semaphores are very useful for is coordinating the execution of 2 processes. So in this example, it's in the book, let's say you have 2 processes, process P1 and P2, and then you have 2 semaphores, S1 protecting critical section 1 and S2 protecting critical section S2, right? And these are semaphore variables. And so suppose process P1 and P2 are executing concurrently, right? Now, of course, they're both on the ready queue, and you don't really know which particular process, whether it's one or two and then one, you don't know the order in which the short-term scheduler is going to select them, right? You don't. So how do you get a certain execution order, right? You have S1 happening first and S2 happening second. How do you get a specific execution order if you don't know what order P1 and P2 are going to be executing, right? These processes. And so one thing you could do is use semaphores to block P2's execution until P1 is done in doing its part, right? And you can use semaphores to do this coordination. So here we have P1, and we have this sync semaphore initialized to 0, right? And P1, it's going to do a signal on this semaphore, right? Because the signal increments the semaphore. And P2 is going to do a wait on the semaphore. Now remember the behavior. So this semaphore, right, variable, if it's equal to 0, execution of the process that does the wait is going to block. It's going to busy wait. Its execution is not going to proceed past this point in that wait command. And the signal, it's going to unlock it. So what they do to do this coordination, you say, okay, well, these are two processes, and we have a semaphore. It's a shared variable, right? And the atomic instructions are wrapped around this wait and signal. So we know that when you execute the wait and signal, it's not going to preempt you off the processor. So they're going to execute. And we start out, if we set the semaphore variable sync to 0, we're sort of pre-locking it, right? It's always locked. And here we have P2. It's going to wait on this pre-locked semaphore. Process P1, it's going to unlock it when it's done with its execution, okay? So here, it doesn't matter if P2 executes first. What does it do? It waits. It's busy waiting. And it's in that while loop, blocking, 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 waiting, 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 because sync is equal to 0. And then eventually, it's going to be scheduled off the processor, right? Okay. Now, P1, it comes along, it performs some operation S1, and then when it's done, it signals that semaphore. And when it signals that semaphore, the semaphore variable gets incremented, so it's no longer 0, it's now 1, and then P2 unblocks, and it executes S2, right? And so you can use semaphores between processes to synchronize a particular order of execution, even though at the end of the day, you have no idea if the scheduler, short-term scheduler selected P1 to execute, then P2, or P2 to execute, then P1. Does that make sense? Any questions about this? So that's kind of nice. Using these semaphores, you can coordinate execution between processes to enforce a particular order of events happens, even though you have no idea which process physically runs first and which physically runs second. Okay? All right. Make sense? All right. So let's continue. So we have this wait in the signal, and you have to guarantee that no two processes can execute wait and signal on the same semaphore at the same time. And what does that mean? It means these things are atomic, right? The underlying variable, you must have either process 1 interact with it first and then process 2, or the underlying variable itself, which goes to your question, that implements the semaphore, that has to be protected. It is a critical section. And so the implementation of this critical section problem, um, in the implementation of the wait and signal, the variable itself used for the counting in the semaphore, it itself has atomic instructions wrapped around it so that its value, all processes understand the same value, and we don't have that same issue, that race condition that we talked about when we first started talking about synchronization. So in this implementation, you have busy wait, and busy wait is not the best way you can implement it, but the idea is that you're only doing so few things to it. It's relatively fast, even though you have the busy wait as an approach for implementing. And so applications that spend a lot of time in your critical section, this is not a good solution, right? If you're doing busy wait as a way of blocking execution from happening, right? The better way to do that is, of course, to reclaim that process from the processor. to actually kick it off the processor to go from ready, from executing to waiting, right? And so this is what most modern systems do. And when you eliminate busy waiting, now you need other data structures, right? And so here you have a modern implementation of a semaphore, and a semaphore variable, instead of just being an integer, it has two things. It has an integer, which describes excuse me, the number of copies of the resource in the critical section, but it also has an array of process control blocks, right? And so now, instead of having these processes busy wait in the acquire implementation, now they're physically waiting. And if you're physically waiting, now you need a wait queue, right? And that wait queue is associated with a semaphore. So it's almost like you're treating the semaphore like it's an I/O device, and processes are waiting for this semaphore. And then when you do the signal operation, you're waking up one of the processes. So you're going to select a process. It's no longer on this wait queue, goes back into the ready queue, and it can now run and access the critical section. So that's now a difference, is to save processor cycles. Instead of doing this busy wait, you're physically waiting, and you're treating the semaphore as if it were an I/O device. Okay? All right. So you have two operations. You have a blocking operation, and what this does is that instead of busy wait or spin locking, you're placing the process that invoked the acquire on the appropriate wait queue, right? And this semaphore variable, now you've introduced a list of process control blocks, and it acts like a wait queue for an I/O device. And then you also have the wake up, right? When you do the signal, you're going to remove one of the processes from this wait queue, this array of process control blocks, and then it's going to join the ready queue so that it can be selected by the short-term scheduler and be and execute on the processor. Okay, so this is an example, and this is pseudocode of the wait and the signal, what it would look like now using this wait queue associated with the semaphore variable. And this is in contrast to the spin lock version of it. And the reason why you want to use this is because it's much more efficient if you're making heavy use of the acquire and the signal. Now, this is, an example of that is, let's say you have a thread pool, right? And you have a high performance server, and you have a lot of incoming requests. You're going to be spending a lot of time with that thread that handles the request and adds it to a queue. You're going to be spending a lot of time doing synchronization, the wait and signal, wait and signal, wait and signal, right? And so if that's the case, you're better off, when you're doing the wait, not having things spin lock to wait. You're better off having it actually block the process, and therefore the semaphore variable acts like an I/O device. So here we have the wait, excuse me, and we have the semaphore variable here passed into the wait. Now, again, these are atomic instructions, right? And so in the implementation of wait and signal, these functions are going to execute to their completion and will not be preempted, right? So we don't have to worry about critical section problem as it pertains to the semaphore variable, which is a C struct that has an integer and it has an array of process control blocks. Okay, so we start out with the wait, and we take our semaphore's value, that integer, and we decrement it. And then we check to see if the value has gone negative. If it's gone negative, that means we don't have any more copies of this bounded number of resources for our critical section. And if it is less than 0, then we add the process that calls this wait to the wait queue associated with the semaphore variable, its process list, and then you block, right? So when you block, of course, you go from from running to waiting, and you're added to a queue, and then you're waiting for someone else to wake you up, okay? So then some process is in the critical section. If the other processes that can't get into the critical section are waiting, that means some process that is done with the critical section is running. So that process called signal, when it is done with the critical section, so what does it do? It increments the semaphore's variable value by 1, right? So if it were 0 or negative, it would now become 0. And then it selects a process from the list and wakes it up. And when it wakes it up, it goes from waiting to ready, and it joins the ready queue and is eventually selected by the short-term scheduler for execution. Okay? Any questions about this? Make sense? So we contrast this version of signal and wait with the version a few slides ago that used spin locks. It's the same behavior, but the mechanism for waiting, in this case, it was very primitive. You're in a while loop that does nothing, a spin lock. Yes, when you execute wait, that process that doesn't have access to the resource, its execution will not continue past that wait call. In this case, it's more sophisticated. And instead of saying execution will not continue, execution physically stops because it's now in the wait queue, this list of process control blocks. And that wait queue is associated with the semaphore itself, and its implementation takes form as a list of process control blocks. Does that make sense? Any questions about this? So you can imagine the process that is finishing the critical section calls signal and ends up, as a result, waking up one of those waiting processes that couldn't enter the critical section. Okay. All right. So deadlock. If you're going to deal with locking, you have to look at this issue of deadlock. And deadlock refers to the relationship between processes that are blocked because they're using locking, but in order to continue, they're waiting for someone else's that's blocked. So you have something I want, I have something you want, but we're both waiting on each other and not making any progress, right? And that's called deadlock. So in this case, we have two processes, P0 and P1, P0 on the left and P1 on the right. And let's say we have two semaphore variables, and let's say these are implemented using blocking, right? So they're going to each have a wait queue associated with them. And P0 starts out and waits on S, right, the first semaphore, and then waits on Q. And P1 waits on Q and then waits on S. Now, of course, if you do a wait, again, to remind you, you decrement that semaphore's count, right? And let's make the assumption here that these semaphores are initialized to 1, both of them. And because they're initialized to 1, this is the behavior of a mutex. Only a single process can enter the critical section. So what happens? So we have S is 1, the semaphore, its value is 1, and Q, its value is 1. So P0, it calls wait on S. So it proceeds to run, and now S is 0. P1 calls wait on Q, right? So let's say these happen at the same time. So after this first line of execution, S is now decremented and Q is now decremented. So after that first line that P0 executes and P1 executes, they're both S is 0 and Q is 0. So now P0 calls wait on Q, right? And because it was initially 1 when they both did the first waits, they're allowed to proceed. So when P0 calls wait on Q semaphore, at that moment Q is 0 because P1 already called wait on Q, right? And it decremented it from 1 down to 0. So at that point, P0 blocks, right? It's put on the waiting queue associated, the wait queue associated with semaphore Q. And then P1, when it executes wait S, well, S has already been decremented from 1 to 0, its semaphore, by P0 when it called wait. So then P1 is going to block and join the wait queue for semaphore Q. So here we have P0 is now waiting, P1 is now waiting, and they can't wake up because there's nobody there to call the corresponding signal. Does that make sense? And so that situation is called deadlock. And whenever you're doing locking, right, and in high performance applications, you want to lock your resources, it's really important to track the dependencies between all the processes as they're engaging in all these different tasks with synchronization. It's important to track your dependencies to check for deadlock, right? And you can imagine, we're just talking about two processes, but you can imagine something like a web server where you're interacting with a database. You want to lock the database, or do you lock records on the database? If you have an incoming request queue, do you lock the whole queue, or do you lock regions of the queue? If you have certain other devices that they might make use of, like callouts to other servers, do you lock that callout, or what do you do? So if you have all these interacting parts here, it's very easy to have a deadlock situation, and you always look at the dependence of one critical section's access on other critical sections. And if you can access multiple things in multiple ways, you want to make sure that you don't have a type of dependence where one process can grab a lock on something, need something else, where another process can access that, grab the lock. Okay, so that's called deadlock. We're not going to cover it in detail for this class, but it's really important, and I'll just say it this way, that you want to track the dependencies that you need when you're engaging in multi-threaded and multi-process applications. And so how does that manifest in a real application? Well, you take all the data structures and all the things that your processes and resources they need in order to operate. You look at the sequence of accesses that you need. You take all those things that are parallelizable and you enforce that sequence by locking at the right resolution or granularity of locking. Do you lock one thing at a time or do you lock multiple things at a time? If you lock one thing at a time, well, you can parallelize, but if that introduces some ordering of execution that leads to deadlock, then you probably want to lock them or use a semaphore to coordinate them. Okay? And so this is more of a practical issue, but it's a real issue, especially as you write high performance servers. So then, of course, if you're doing the signaling, it doesn't matter what comes next in these executions. Both of these processes, P0 and P1, are going to be blocked here because P0 is waiting for P1 to signal, P1 is waiting for P0 to signal, and nobody's making progress, and the whole system freezes. Nothing's happening. Okay? All right. Any questions about this? Does that make sense? All right. All right, we have 15 minutes. So this idea of deadlocking and starvation, deadlock is the cyclical dependency. I want something you have, and you want something I have, and we're both waiting for the other person to free up the resource, and therefore nothing happens. This starvation talks about this indefinite blocking, that you're never removed from the wait queue of the semaphore because it's suspended, and the thing you're waiting for is also suspended, right? So that means everybody stops and nobody makes any progress, nothing happens, right? And that's a particularly hard thing to debug. You find out when it happens, but it's kind of hard to debug. And then there's also something called priority inversion. Let's say you have a bunch of locks and your processes or threads have different priorities. By nature of how priority scheduling happens, that there's a preference in the scheduler for the higher priority process or thread. Now, of course, if it gets the processor first, it's going to execute the acquisition of the lock before the lower priority process does. And in that case, you can get this idea of priority inversion in that even though you have a certain priority, the locking system is kind of flipping that, right? And so priority inversion is a scheduling problem when a lower priority process holds a lock needed by a higher priority process. So the higher priority process could certainly possibly starve out the lower, but then eventually the lower priority process is going to acquire the lock to a critical section. And the higher priority process, it's selected by the short-term scheduler more often than the lower priority by definition of what priority scheduling is. And it says, okay, I'm ready to run because I'm higher priority. And all of a sudden, it can't run and it blocks in the wait queue associated with a semaphore because a lower priority process is now has acquired the lock, right? And so that's a problem. So in addition to this idea of starvation due to deadlock, you can also have issues associated with so-called priority inversion. And one solution for that is that if a higher priority process is waiting or it has to wait because of it doesn't have access through a semaphore, you can temporarily give that lower priority process the higher priority of the waiting process. And so you boost its priority momentarily so it gets done faster with the critical section and releases the lock. Okay? And so if it sounds like it's complicated, yes, it is complicated. And you can imagine how that might happen in an operating system. When you call the wait function on a semaphore, you're also checking priorities for the processes that are in the critical section as well as the processes that are waiting to gain access. So it's a lot more complicated, but Depending on your application, it's something that you would uh, have to implement because it's a real problem. Okay. Any questions about this? Does that make sense? Yeah. All right. So problems with semaphores. You can have incorrect use of semaphores. So if you signal a mutex before, and a semaphore is the same as a mutex. If you set the count to 1, semaphore behaves just like a mutex. A mutex you can think of as a special case of a semaphore where the semaphore is variable, representing, bless you, the counts of the number of copies of critical section resources is equal to 1, right? And so if you signal the mutex and then wait for the mutex, that's incorrect. And if you wait for the mutex, then wait for the mutex, that's also incorrect, right? So you could certainly have incorrect use of these synchronization mechanisms, and that's a programmatic thing. Or let's say, you do a wait, but you don't have the corresponding signal. So you lock the resource, use the critical section, and then walk away and don't do anything, right? That's a problem. And so still, these synchronization mechanisms, there's no magic involved. You have to, as a software engineer, you have to use them properly in your programs. Okay. All right. So let's take a look lastly at monitors. Um, and a monitor is a high-level abstraction, and it's provided typically in the language runtime. Java has a very nice implementation of monitors. And what the monitor does, when we have these semaphores, right, we have a wait queue and you have access to a critical section, and you can have more than one process access the critical section, and that bound on the number of copies of a resource in the critical section is encoded by the semaphore variable. And then when you acquire, you decrement, and when you signal, you increment. Now, a monitor kind of looks a lot like a semaphore. It also has this idea of blocking, but now if you want more sophisticated control of who you block and who you unblock, semaphores can't really do that, right? And so that's what a monitor is really good with. You can have more sophisticated ways of interacting with wait queues, and you can define what are called condition variables. And these condition variables you can think of as variables that are associated with their own wait queues. So suppose, you have some processing, and let's say, you have a bunch of subtasks, and those subtasks are assembled as a sequence of things that have to be done in some processing pipeline. So let's say one task is to load an image, another task is to maybe compute the color histogram of the image, and then another task is to extract background objects depicted in that image, right? It's some computer vision application, for example. So let's say, you have one semaphore used to take these raw tasks off to load the image, right? So you load the image, you put it into shared memory, and then you're going to hand it off to the next stage of processing. Now, of course, if you have a thread pool, right, you might have a pool of threads or a group of worker threads that are calling the function that knows how to compute the colors on these images, right? So you have one team of people, each one of which can process color. And then another group of threads in a thread pool that can, for example, extract the background information, right? And so you have these two groups that can perform certain tasks. When the first task of loading the image is done, you don't want to just wake up any thread. You want to wake up a certain group of threads and have somebody picked who's going to do that next stage of processing. Let me draw that on the screen, on the board here, to kind of make it a little bit more understandable. So let's say you have some task, and that job or that process consists of task one, task two, task three, right? And let's say, task one is loading an image, task two is analyzing color of the image, and task three, let's say, is getting the background, right? So you have some complex task, and that complex task consists of task one, task two, and task three. So let's say, the first thing you do is you load an image. When you load an image, let's say you have RAM and you're using shared memory to load your image, image one, and it's in RAM. So if it's in RAM, you have an array of these images. Here's the next image, image two, image three, and so forth, right? So let's say you're rendering video, right? You're cutting some video and you're analyzing the frames. Let's say you're colorizing a video. You're taking a black and white video and frame by frame, you're converting all the black and white stuff in the image, the grayscale, into color, right? They do that a lot with old time movies. And so you have a bunch of images and each image represents one frame of video. Video is nothing more than the display 30 times a second of images. And the first thing you want to do is load the image. Okay. Well, this array in RAM, this array of images, image K, that's a critical section, right? Because you can have multiple threads. Say if you have a thread pool, and let's say you have more than one thread, and I'm just going to draw a thread as this kind of curly arrow here. And you have a bunch of threads that are trying to access this critical section, this array, and their job is to take something off disk and load it into the array, right? All right. So after an image is loaded into the array, let's say the next one is to now take an image and do some color analysis. And let's say you have, this is the pool for loading, the loading pool. And let's say this is the color analysis and now analysis pool. And this has a bunch of threads, right? And this is now the background thread pool, BG pool. Okay, so now each one of these threads are trying to access critical section. The load pool, is going to access this critical section. And let's say the color analysis, let's say there's another array, and that's going to store the color analyzed version. And then the background version is another array, right? So you have three different critical sections, and you want to use a semaphore or some synchronization mechanism to control the access of these multiple threads in the thread pool to each one of these critical sections. So let's say these are waiting, and this is the load semaphore. So load semaphore. This is the color semaphore, and this is the background semaphore or synchronization mechanism. So now, let's say in the beginning, there are no loaded images that the color can work on, right? And let's say there's no information that the background pool can work on. So all of these are blocked. Now, the moment that you have an image here, one of these now has work that it can work on, right? Now, with the existing semaphore that we talked about, each one of these is on a wait queue, right? It's just sitting there waiting. And it doesn't get put back on the ready queue until someone calls signal. Now, when you're doing the signaling, well, the moment that this one thread here in the load pool has entered the critical section, and it's what it does in the critical section is it puts an image in that shared memory. At that moment, you want to wake up one of these, right? And so they're all waiting, but for a given semaphore, you can only wake up somebody on the same wait queue. You can't wake up someone on a different wait queue, right? And so the monitor solves that problem. And with a monitor, you have this thing called a condition variable. And this condition variable is associated with a wait queue so that now you can say, okay, the moment this load thread is done with a critical section, putting an image into memory, now it can wake up a different wait queue to cause one of these to now take it and analyze the color, right? And so if you want to have multiple wait queues and wake up not just your group of threads, wake up a different group of threads, you're going to need another access to that other wait queue. And that's done in a so-called monitor. Does that make sense? And so a monitor kind of looks like a semaphore. It's a special, weird kind of semaphore where you can have multiple wait queues. And those wait queues are associated with something called a condition variable. And Java implements this quite well. Okay? All right. So what do we have? A monitor is a high-level abstraction, and it's very effective for synchronization. But moreover, it has these internal variables that can access code, so it has functions you can perform on this critical section, and it also has internal variables that you can associate ultimately with these wait queues. And so only one process at a time can be active in the monitor. Okay, that's a given. It's a synchronization mechanism. So this pseudocode kind of depicts this idea that not only do I have the locking mechanism, right, where I can bound my resource, I also have a library of functions that I can exercise on this resource, right? So the monitor has multiple wait queues. It has a library of functions that you define, all the operations that you can perform on the critical section, as well as these shared variables, okay? So let's take a look graphically what a monitor looks like. You have some shared data. You have the operations that you can perform on the shared data. And then you have this entry queue. This entry queue you can think of as the wait queue, and that wait queue are all of those processes or threads that want to gain access to the critical section. So now, this idea of condition variables allows you to associate different threads or processes with different wait queues. So imagine if I had a wait queue here, right? And I had a wait queue here and a wait queue here. Each wait queue is associated with a different condition variable. You can think of a condition variable as being a different wait queue, right? So with these condition variables, you have two operations. You have a wait. That's the thing that checks if you have enough copies of the resource freely available for the process to execute. And then it also has a signal which restores back, like incrementing the count. So you can almost imagine like you have multiple semaphores. Each semaphore is associated with a condition variable, but you only have a single shared data structure that you're accessing, okay? And it's really, really useful when you're implementing pipelines. You have one stage of processing, hands off to another stage of processing, hands off to another stage of processing, where at each stage you have a pool of threads or processes that are doing something. Okay? All right. Any questions about this? Does that make sense? And so when we come back on Tuesday, we'll actually have an example where we're going to use monitors in Java for our final project. But let's continue to finish out this module. So here now we have a monitor. Oh, that's time. All right, let me finish up in 30 seconds. We have a monitor with condition variables, our processes waiting for entry to the monitor, sit in the queue, and then we have different condition variables. Each one defines its own wait queue, right? And so now, based on the operations we're running, we can have subsets of processes or threads in one associated with one queue. You can now wake up a different process associated with a different queue. Okay, it's a really powerful mechanism for writing high performance servers. So let me end here in the interest of ending on time. And we will pick back up on Tuesday. Have a safe and boring, restful Thanksgiving holiday. And please travel safely there and travel safely back. I really mean that. All right. Want to see you here intact on Tuesday next week. All right. I'll see you then. Take care.